Hello everyone, welcome to Quantitative Reasoning. My name is Elaine Tintoni. I'm the lead online math instructor at ICC. I'm going to be going through the entire Quantitative Reasoning course with you, and we're going to get started today in section 2.1. So in chapter 2, we're learning about set theory, and in section 2.1, we're going to start with basic set concepts. So in this first section, here's what we will look at together. We're going to talk about 3 methods for representing sets. We're going to learn how to define and recognize the empty set. We're going to learn some symbols. We're going to learn about the natural numbers, what it means to determine a set's cardinal number, and how to recognize equivalent sets, equal sets, finite, and infinite sets. And so here we go. So first, let's just start at the beginning. A set is a collection of objects whose contents can be clearly determined. The objects in a set are called the elements or members of the set. And a set has to be well defined, meaning that its contents can be clearly determined. In other words, it can't be left up to opinion at all. The order in which the elements of the set are listed is not important and makes no difference. If we rearrange the elements of the set, it's still the same set. So here we have example 1, and this says, decide whether the following describe well-defined sets. Give a reason for your answer. And in part A, it says Paris, London, and Lima. Now at first glance, this might seem like a well-defined set, but then if you find out that there are multiple cities with each of these names, then when you look at the list, you think, well, I don't know which Paris and which London and which Lima are being referred to. So it turns out that this is not a well-defined set, and the reason is that there are multiple towns with these names. In part B, we have Paris, Mississippi, Lima, Montana, and London, England. And so now with the states and countries listed, it's very clear which towns are being referred to, and so we can say that this is a well-defined set because there cannot be any confusion about which towns are meant. In part C, it says the good students in your math class. Well, this is not a well-defined set because different people might mean different things by the word good. So one person might say that a good math student is one who shows up every day and tries really hard and always pays attention, and it doesn't matter what they make on the tests. And another person might say, well, a good math student is somebody who always has good grades on the test. And so there can be 2 different opinions, and that means that this is not a well-defined set. Okay, let's talk about how to represent sets. Capital letters are usually used to name sets, and there are 3 methods that are commonly used to designate a set or to define what things will be members of the set. One way to designate a set is a word description. So like you just literally say in words what belongs in the set. Another method is called the roster method. And the roster method is just simply making a list of every element of the set. And then the third way is called set builder notation. Now, set builder is most useful when we're talking about sets of numbers or sets that are mathematically defined, but we will do an example with other types of sets as well so that you can see how set builder notation works. Okay, example 2. Write a word description of each of the following sets. So first, let's read each set, and then we'll think about what words might best describe that set. So whenever we encounter these curly braces, we will read that as the set containing. So here in part A, it says P equals the set containing Washington, Adams, Jefferson, Madison, and Monroe. Now, if you remember your history, you might recognize these 5 names as the names of the first 5 presidents of the United States. So we could say that P is the set of the first 5 presidents of the U.S. Now, there are no magic words. If you said the set containing the first 5 presidents, or if you said the first 5 presidents of the United States of America, you know, there are different words that we can use as long as your meaning is clear. So I don't want you to feel like there are any magic words that have to be said. All right, in part B, we have S equals the set containing Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And we recognize these as the names of the planets in our solar system. So we can say that set S is the set of planets in our solar system. And then in part C, we have J equals the set containing January, June, and July. And so clearly those are months of the year, and it appears to be all the months that begin with the letter J. So we could say J is the set of all months that start with the letter J. Okay, now let's take a look at the roster method. So the roster method, like I said before, is another way of representing sets, and it just means to make a list of all the members of the set. We use commas to separate the elements of the set, and we put the elements inside these curly braces. You saw that in the last example. So if we say that W is the set of the days of the week, that's a word description. And then using the roster method, we could say W equals the set containing Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Now, just to reiterate, even if I were to state these 7 days of the week in a different order, it would still be the same set. It would still be the set W. So the order has nothing to do with it. This just happens to be the order that we see on our calendars. Okay, now in example 2, we had a set that was described with the roster method, and we had to give the word description. Now in example 3, we're going to have a set where the word description is given, and we will have to come up with the roster method. So it says express each of the following sets using the roster method. And part A says set C is the set of U.S. coins with a value of less than $1. Okay, well, you think of all the coins that we use that are worth less than $1. So we would say C equals the set containing, let's just start with the smallest. So the smallest one is a penny or a cent. And the next one is a nickel, then a dime, then a quarter, and we don't see them very often, but there are $half also. And so those are all the U.S. coins that are worth less than $1. Notice the curly braces. That's important because everything inside these curly braces will be considered a member of the set. And again, keep in mind that even if we listed these in a different order, it would still be the same set. All right, part B says set S is the set of 4 seasons in a year. So we could say that S equals the set containing, and it doesn't matter which order you list these in, but I'm going to put winter, spring, summer, and fall. And then in part C, set M is the set of months that have exactly 30 days. All right, so we'll say M equals the set containing, and let's just go through the calendar, okay? So January has 31 days. It won't be part of the set. February only has 28. March has 31, but then April has 30 days, so April is part of the set. May has 31, June has 30, all right, then July 31, August has 31, September has 30 days, so it's part of the set. Then October has 31 days, November has 30 days, and December has 31. So M equals April, June, September, and November in any order that you choose. And our last method for representing sets is set builder notation. And set builder notation looks like this. Now again, set builder notation is much more useful for sets that contain numbers, for sets that are mathematically defined. And so I think when we go through these examples, you'll think, well, this is not any better than the word description, and you'll be right. But this is not the best use of set builder notation. We're just doing this example so that you can see how it works. So with set builder notation, again, we have the curly braces, but we have this vertical line. Okay, so this would be read as the set W is the set of all elements X such that X is a day of the week. Now, the vertical line is always read such that. And what's happening here is that before the vertical line is the variable, in this case x, which represents an element in general. And after the vertical line is a condition that x must meet in order to be an element of the set. So again, W equals the set of all elements x such that x is a day of the week. And from that we know that W is the set containing Sunday, Monday, Tuesday, Wednesday, etc. Okay, now let's look at an example. So this says express each of the following sets using the roster method. So we know that means just to list all the elements of the set. So in part A, it says that the set A is the set of all elements x such that x is a month that begins with the letter M. Okay, so we will write A equals the set containing, and now if we think through the calendar, we only have 2 months that begin with the letter M, and so that would be March and May, and that's all the elements in our set. And so moving on to part B, we have the set B is the set of all elements x such that x is a lowercase letter of the alphabet that follows D and comes before J. So using the roster method, we could say that the set B equals the set containing, let's see, follows D, so that would be E, F, G, H, I, and then we wanted any letter that comes after D but before J, so J is not included. That means I is the last element in the set, and we'll just close that off. And so B is the set containing E, F, G, H, and I. Now in part C, we have a mathematically defined set. And this notation might be a little new to you. We're going to see it again in a minute, but for right now, for this example, I'll just go ahead and tell you that this funny looking E here, it looks sort of like an E, this means is an element of, and this funny looking N stands for the natural numbers. So X is an element of the natural numbers is what that means. And you remember what the natural numbers are from grade school probably. The natural numbers start with 1, and then after that it's whole numbers. So we don't say whole numbers because that would include 0, but the natural numbers are the counting numbers. So like 1, 2, 3, 4, and so on. Okay, so if C is the set of all elements x such that x is a natural number and x is less than or equal to 5, okay, then C is the set containing 1, 2, 3, 4, and 5 is included here because x can be less than or equal to 5. And so that's our set C. Now let's talk about the empty set. So the empty set is also called the null set, and it is the set that contains no elements. The empty set has no elements, of course. So the empty set can either be represented by this circle with a line through it. I know it looks like a 0, but it's not. It's a circle with a line through it, or it could just be a pair of empty braces. Now, a lot of times we don't use the empty braces because that kind of leaves it open to a question of could there be something missing? Is there a typo? Where the empty set symbol is very clear that we mean a set with no elements. So both ways of writing it have the same meaning. However, we do not want to mix the symbols. We don't want to put the empty set symbol inside a set of braces because that would mean the set containing the empty set. If you just want to say the empty set, you need to either say it this way with just the empty set symbol or this way with just the pair of empty braces. Now here are some examples of empty sets. So if we say that the set A is the set of all elements x such that x is a living person born in 1850, well, there are no people who fit that description. There are no people currently living who were born in 1850. So set A would be empty. Or if we say that the set B is the set of all elements Y, such that Y is a woman who served as U.S. President before 2022, well, that set is also empty, because there could be a woman elected in the future, but there are not any women in history before 2022 who served as U.S. President. So B is also the empty set. And then let's think about set C. This says that set C is the set of all elements X such that X is less than 5 and X is greater than 10. So set C would be the set of all numbers that do both of these things at the same time. But it's not possible for a number to be less than 5 and also greater than 10. So no numbers fit this description, and therefore set C is the empty set. Now, here's example 5, and it says, which of the following is the empty set? Give a reason for your answer. Okay, so in part A, we have the set containing 0. Well, this set contains an element, and that element is 0, so this is not the empty set because it contains one member. Part B is 0. Well, notice that this does not have the curly braces, so this is not even a set, and so it's certainly not the empty set. However, I will say that the empty set contains 0 elements, so this is the number of elements in the empty set, but the number itself is not the empty set. All right, in part C, we have the set containing all elements X such that X is a number less than 4 or greater than 10. This time we have the word or. So our set contains any number that is either less than 4 or greater than 10. Well, there are numbers that fit this description. So just to list a few members of this set, 3 would be a member of this set because it's less than 4. 2 would be a member, 1 would be a member, 11 would be a member of this set because it's greater than 10. 12, 13, and so on. And we could list an infinite amount of numbers that would be members of this set. Okay, in part D, we have the set of all elements X such that X is a square with 3 sides. Now we know that you can't have a square with 3 sides. A square has 4 sides. And so there are not going to be any elements X that fit this description. That means that this set has no elements, and that means that this set is the empty set. Now let's go back and talk about notation a little more. So we saw this symbol earlier. It looks like a funny looking E. It is not an E, so I don't want you to read it as E. However, it is a symbol that looks like an E, and it's used to indicate that an object is an element of a set. And so that symbol is used to replace the words is an element of. Whenever you see this symbol, you should read that as is an element of. And the same symbol with a line through it is used to indicate that an object is not an element of a set. So whenever you see this symbol, it should replace the words is not an element of. So let's practice a little bit. So it says determine whether each statement is true or false. And so part A says that the letter lowercase r is an element of the set containing A, B, C, and so on, all the way to Z. Now, the R is not written here, but the 3 dots tell us that everything that would normally come between C and Z is included in this set. So R is a member of this set, and therefore that statement is true. In part B, we have the statement 7 is not an element of the set containing 1, 2, 3, 4, and 5. And that is also true. 7 is not a member of that set. So we'll put true there. And then in part C, now notice the curly braces here, so be careful when you're reading. This says the set containing A is an element of the set containing A and B. Now, notice that A is a member of this set and B is a member of this set, but the set containing A is not an element of this set. You see the difference? So this statement is actually false. However, it would have been true if they had said A is an element of the set containing A and B. That would have been true. But the set containing A is not an element of the set containing A and B. Okay, now let's talk a little bit more about the natural numbers. So, like we said before, the numbers we use for counting are the natural numbers. And the set of natural numbers is represented with this funny looking N. This way of writing an N is called blackboard bold. And it's just a way of writing the N so that it differentiates it from just a regular capital N, so that we know that what's meant by is the set of natural numbers. And so the way you can write this on your paper is you can just make the left side of your N like that, and then for the middle part put those two lines, and then the right side. And that's how I make my blackboard bold when I'm writing on my paper. So now look at the three dots that come after the last element, and those three dots are called an ellipsis. And the ellipsis after the 5 indicates that there's no final element, and so the list goes on forever. So it would also include 6, 7, 8, etc. on forever. And therefore this set is an infinite set. Now let's look at example 7. So it says express each of the following sets using the roster method. So we will have our capital letter of this that names the set equals, and then our curly braces, and then we'll list all the members. Okay, set A is the set of natural numbers less than 5. So we will put A equals the set containing the natural numbers less than 5. So we remember that the smallest natural number is 1. So we'll have a 1 there, comma, 2, and we'll go all the way up to 4, but then we don't want to include the 5 because it says it's the set of natural numbers less than 5. So the 5's not included. 4 is the last member, and so we'll put that closing curly brace on there. Okay, and then part B. Set B is the set of natural numbers greater than or equal to 25. So we will have B equals the set containing, now greater than or equal to 25. So 25 will be the smallest member of our set, and then we could list a couple more. We could list 26 would also be a member, 27 would also be a member, but we don't want to keep listing numbers forever because there's an infinite amount of these numbers that are greater than 25, and so what we'll do here is we'll just put our 3 dots like that, and that will indicate that the set goes on forever, but then we'll put the closing curly brace there. Alright, in part C, we have the set E is equal to the set of all elements X, such that X is an element of the natural numbers and X is even. So we want to include all the natural numbers that are even or divisible by 2. Okay, so we will say E equals the set containing the natural numbers that are even. Now the smallest natural number is 1, and that's not an even number. So the next natural number is 2, and 2 of course is even. And so after that we have 3, which is odd, and 4, which is even, and then 5 is odd, but 6 is even. So far our set contains 2, 4, and 6, but we don't want to keep listing numbers forever, so now we'll just put our 3 dots and close the set. Okay, now a lot of times when you're dealing with set builder notation, numbers will be described with inequalities. So let's just kind of look at the different types of inequalities we can have. We are familiar with the less than sign, so this inequality says x is less than a. In set builder notation, you could possibly have a set like this, where it says the set of all elements x, such that x is a natural number and x is less than 4. So of course that would include the 1, the 2, and the 3. Or if we use a less than or equal sign, then in our set builder notation, if we have x is less than or equal to 4, that would include the elements 1, 2, 3, and 4. We could have a greater than symbol. So the natural numbers that are greater than 4 are 5, 6, 7, 8, and so on. But if we have that or equal to bar under the greater than symbol, so if we have x is greater than or equal to 4, then we would include the 4, see? So the natural numbers that are greater than or equal to 4 would be 4, 5, 6, 7, and so on. Now we also can have sets defined by what's called a compound inequality, meaning that any element of the set has to satisfy two inequalities at the same time. And both inequalities will always be written with either less than or equal to symbols. You won't see greater than symbols used in these compound inequalities. So let's start by looking at this one, which says that A is less than X, which is less than B. Now another way to think of this is that X is stuck between A and B. See, the A has to be the smallest number. A has to be less than the element in our set, and the element has to be less than B. So for our example, we have 4 is less than X, which is less than 8. Well, if you think about the numbers that are between 4 and 8, but they can't be equal to 4 or equal to 8, then that would be 5, 6, and 7. See, 5 is both greater than 4 and also less than 8. Same for 6, the same for 7. And so those three numbers satisfy this compound inequality. If we put or equal to bars underneath the less than symbols, then we have 4 is less than or equal to X, which is less than or equal to 8. So all that happens here is that we're still capturing the numbers between 4 and 8, but now the 4 and the 8 are included. So if 4 has to be less than or equal to our element, then 4 is an element because it satisfies the or equal to part. And 8 is also an element because it satisfies the or equal to part. 5, 6, and 7 are still in there because they're still between 4 and 8. You also can have it set up where there's an or equal to bar on either the first inequality or the second one. And so for this one, where you have 4 is less than or equal to X, which is less than 8, then you can have the element 4 in your set because that's the or equal to part. It says that 4 can be equal to your element, and so 4 is there, but also 5, 6, 7, but notice that 8 is not there because it does not have the or equal to part. On this last example, if we have 4 is less than X, which is less than or equal to 8, you see that the or equal to bar is with the 8, and so 8 is included where 4 is not. So example 8, so this says express each of the following sets using the roster method. And part A says the set of all elements X such that X is an element of the natural numbers and X is less than or equal to 100. Okay, so the roster method, that's where we list all the elements. But of course, we're not going to list all these elements. We're going to use the ellipsis so that we don't have to write so many numbers. So X is an element of the natural numbers. We know the smallest natural number is 1. So we will say that this set includes 1, 2, 3, and then it includes all of the natural numbers that are less than or equal to 100. But I don't want to write all those numbers, so now we'll put ellipses. We do need to put the final element to show that the set stops there, and then we put the closing curly brace to finish the set. And for part B, we have the set of all elements X such that X is an element of the natural numbers, and 70 is less than or equal to X is less than 100. So X is stuck between 70 and 100, or in other words, all of the elements of our set are between 70 and 100, but one of our elements can be 70 because of this or equal to bar. So we'll say that the set includes 70, 71, 72, and so on, all the way up to, not 100, because notice that the set does not include 100, but 99 would be the biggest natural number that is less than 100, and then we would close our set. Now let's talk about cardinal numbers. So the cardinal number of set A, which is represented by n parentheses A, is the number of distinct elements in set A. Distinct meaning that we don't count any repetitions as extra elements. So whenever you see n parentheses A, that's actually read n of A. N of A. Again, repeating the elements in a set does not add new elements because we're only counting the distinct elements. And because repeating the elements does not add new elements, repeating them does not change the cardinality of the set. So the cardinal number just represents the number of different or distinct elements in the set. Okay, so example 9 says find the cardinal number of each of the following sets. So if set A contains 7, 9, 11, and 13, then there are 4 elements in this set. So we will write n of A equals 4. Or another way to say that is the cardinality of A is 4. Now when you do your homework in my lab and they ask you what is the cardinality of the set, you just want to say 4. You don't want to say that the cardinality of A is n of A equals 4, because when they ask you what the cardinality of A is, they just want the number. So you can either say n of A equals 4, or you can say the cardinality of A is 4, but don't say the cardinality of A is n of A. Okay, that's just doubling up notation. You don't need to do that. Here in part B, we have the set B is equal to the set containing 0. Now there's one element in that set, so n of B is 1. For part C, we have the set C is the set containing 13, 14, 15, and so on up to 23. So you can just count. 13 is the first element, 14 is the second element, 15 is the third element, and so on. If you count the elements all the way up to 23, you'll find out that n of C is equal to 11. And then for part D, we have the empty set. So the empty set, by definition, contains no elements. So the cardinality of the empty set is 0. Okay, now that we know about cardinality, we can talk about equivalent sets. Sets that contain the same number of elements are said to be equivalent. Now, not equal, but equivalent, okay? So for us, those two words have different meanings. Sets that contain the same number of elements are said to be equivalent. So if we say that set A is equivalent to set B, that means that set A and set B contain the same number of elements. In other words, for equivalent sets, n of A will equal n of B. Equivalent sets have the same number of elements, so their cardinality is the same. Okay, these are equivalent sets. Here we have two sets A and B, and set A is all elements X such that X is a vowel. Well, there are 5 vowels in the English language, A, E, I, O, U, so there are 5 elements in set A. And then in set B, we have the set of all elements X, such that X is an element of the natural numbers, and 3 is less than or equal to X is less than or equal to 7. So every element of our set is between 3 and 7, but the elements also include 3 and 7. So our elements are 3, 4, 5, 6, 7. And notice that we can match up each element of set A with an element of set B. So the arrowheads indicate that each element of set A can be paired with exactly one element of set B and the other way around. So they're an exact match. That means their cardinality is the same. That means they are equivalent. It does not mean that they have the same elements. You can see that the elements are different. So they're not the same set, but they have the same number of elements, so they are equivalent. So the arrowheads on the previous slide indicate what we call a one-to-one correspondence. If set A and set B can be placed in one-to-one correspondence, then A is equivalent to B. In other words, the cardinality of A is equal to the cardinality of B. So a one-to-one correspondence means each element in set A matches one element in set B, and the other way around. Now, if set A and set B cannot be placed in one-to-one correspondence, then set A is not equivalent to set B, and we would write n of A is not equal to n of B. Okay, here we are at example 10, and this says the figure shows the top 5 impediments to academic performance for U.S. college students. Let set A equal the set of 5 impediments shown in the figure. Let set B equal the set of the percentage of college students reporting each impediment. Are the sets equivalent? And we want to explain. So we're going to look at this 2 different ways. So one way to determine if the 2 sets are equivalent would be to use the roster method to list the elements of each set and see if we can set up a one-to-one correspondence. And so the elements of set A are the 5 impediments, and we get those from the horizontal axis labels here. So set A is the set containing stress, sleep, illness, anxiety, and work. And then set B is the set of percentages of college students reporting each of those impediments. So set B is the set containing 28, 20, 19, and here's another 19, but we don't list it again because remember that repeating the elements in a set does not affect the cardinality. So the second 19 does not add anything to the set, and then the last element is 14. And then we want to see if we can set up a one-to-one correspondence here. So the stress element in set A matches the 28 in set B, the sleep matches the 20, and the illness matches the 19, but then there are 2 elements left in set A and only 1 element in set B. So the anxiety, you can see from the graph, actually matches the 19. That means there are 2 different impediments that match the same percentage, and therefore this is not a one-to-one correspondence, and that means that set A is not equivalent to set B. Another shorter, maybe easier way to look at it is that set A contains 5 elements. In other words, the cardinality of set A is 5, and the cardinality of set B is only 4, because there are only 4 different numbers here. And therefore, since the cardinalities are not equal, the sets are not equivalent. And so here we have example 11, and it says, are each of the following sets equivalent? Why or why not? Okay, in part A, set A contains the elements 1, 2, 3, 4, 5. Set B contains the elements 0, 1, 2, 3, 4. Now both sets have a cardinality of 5, so we can say that the cardinality of set A equals the cardinality of set B, and since they both have the same number of elements, they are equivalent. In part B, we have set A is the set containing 1, 3, 5, 7, 9, and set B is the set containing 2, 4, 6, 8, 10, 12. These 2 sets do not have the same cardinality. The cardinality of set A is 5. The cardinality of set B is 6. 1, 2, 3, 4, 5, 6. And since the cardinalities are not the same, set A and set B are not equivalent. Now let's talk just a little bit about finite and infinite. Set A is a finite set if the cardinality of A is 0, in other words, if A is the empty set, or if the cardinality of A is a natural number. A set whose cardinality is not 0 or a natural number is called an infinite set. So let's look at an example. So this is example 12. It says determine if each of the following sets is finite or infinite. Give a reason for your answer. So part A says set A is the set of all elements x such that x is a natural number and x is greater than 100. Now, there is an infinite supply of natural numbers that are greater than 100. So you'd start with 101, 102, 103, and so on, and it would never end. So we will say that this is an infinite set, and the reason is that there are an infinite amount of numbers that are greater than 100. For part B, we have set B is the set of all elements x such that x is an element of the natural numbers and x is less than 15. Now, as we know, the smallest natural number is 1. So this set will contain all the natural numbers from 1 up to 14, because 14 is the largest natural number that's less than 15. And so there are only 14 of those numbers. This is a finite set. And for a reason, I'm just going to say that the cardinality of this set is 14. And since 14 is a natural number, that set is finite. For part C, we have the set C is equal to the set of all elements x, such that x is an element of the natural numbers and x is less than 10,000. Now this set has a lot more than 14 elements. In fact, it would have 9,999 elements, because we want to include all the numbers between 1 and 9,999, and then we just would not include the 10,000. So although that is a very large amount of elements, it is a finite amount of elements. And so the set is finite, and we'll say that the reason is that the cardinality of the set is 9,999. Now let's talk about equal sets. So if we say that set A is equal to set B, that means that set A and set B contain exactly the same elements, regardless of order or possible repetition. So we don't consider the order or whether anything's repeated or not, but if they contain exactly the same elements, then those two sets are equal. And of course, we symbolize the equality of two sets by putting an equal mark between them. In English now, the word equivalent and the word equal are often used interchangeably, but that is not the case in set theory. Remember that equal sets contain exactly the same elements, while equivalent sets only contain the same number of elements, but the elements don't have to be exactly the same as each other. Now, if two sets are equal, then they must be equivalent, because if they have all the same elements, then they have the same number of elements. But if two sets are equivalent, that does not necessarily mean they are equal, and we saw that on a previous slide where we had the vowels and the numbers. Okay, now let's look at example 13 together. So this one says, determine whether each statement is true or false. In part A, we have the set containing 4, 8, and 9 is equal to the set containing 8, 9, and 4. And we know that the order does not matter when you're determining equality. We just have to have all of the same elements in both sets. So in this case, both sets contain a 4, both sets contain an 8, and both sets contain a 9, and that accounts for all of the elements in both sets, and so we can say that part A is true. In part B, it says the set containing 1, 3, and 5 is equal to the set containing 0, 1, 3, and 5. Now notice that the cardinality is not the same. This first set contains 3 different elements, and this second set contains 4 different elements. So the fact that the second set contains an element that is not in the first set is enough to say that these two sets are not equal, so that statement is false. And now in part C, we have the set containing 4, 5, 6, and 7 is equal to the set containing 5, 4, 5, 5, 7, and 6. Now we know from part A that the order doesn't matter, but also remember that repetition doesn't matter either. All that matters is that both sets contain the same elements. Two sets are considered equal if both sets contain the same elements, regardless of order or repetition. So let's just check it out. This first set contains a 4, and the second set contains a 4. The first set contains a 5, and the second set contains a 5. Now you can see that it also contains a couple of other 5s, but those are just repetitions of an element we've already considered, so those don't matter. And the first set contains a 6, and the second set also contains a 6. The first set contains a 7, and the second set contains a 7. And that accounts for all of the elements. So the bottom line is that order and repetition do not affect equality. So if you ignore the repeated elements and the differences in the order, these two sets are exactly the same. And so this statement is true. Okay, you guys, that is it for section 2.1. What you'll want to do now is return to the Module 1 checklist in Canvas and do the next task in the checklist. Be mindful of the due dates. Be sure to reach out to your instructor as soon as possible if you have any questions. We are always glad to help you. I wish you good luck in the course, and I'll see you in the next video. Bye.